section 3-4 is a great, okay, the problems aren't necessarily fantastic, but it is a great section where we pull all this together and talk about where we could use this in the real world. Now, the problems we're going to be looking at aren't necessarily real world driven, but some of them get close, because here's what happens in the real world. When a business opens, obviously they want to make money. And so one of the things they want to do is figure out, where do we produce to maximize our profit? But another thing that they think about is, where do we produce to minimize our costs? And so those two things kind of work together. But it turns out that all the work that we've done so far has led us right to this. Because all of that shading that you were doing on your homework on section 3.3, sometimes you would find out that when you were done, there was like a triangle shape formed by your double or triple shading. Or maybe some kind of quadrilateral, four-sided figure from that shading. That region is called a feasible region. And a feasible region means, feasible just means basically possible. But that feasible region is where the business wants to be. They want to be producing in that feasible region. And then the question would be, okay, if we're producing in here, where do we maximize our profit? Where do we minimize our costs? And it turns out that those things will always occur at the vertices of the feasible region. So if it's a triangle, we have three vertices that we're going to take a look at, and we're going to say which one of these maximizes profit, which one of these minimizes the costs. And sometimes they don't ask for both. Sometimes they just want one. Hey, let's maximize our profit. But sometimes it gets a little hard to figure out where those spots are. And that's why we talked about using the graphic calculator to find intersections, but we also know we could do it by substitution or linear combination, because those vertices are what we need to figure out where to maximize profit or minimize costs. So right here we've got an example. It says to solve problems using linear programming, our getting ready is you want to spend no more than $40 for at most 15 tomato plants. You want to maximize the pounds of tomatoes you'll get. How many of each plant should you buy? And then justify your answer. And now with this one, we're not necessarily going to go through and solve the whole thing, but I do want to set it up with you, because really we know what to do once we get the word problem set up. We know how to graph those linear inequalities. It's just a matter of getting to that point. So this is something, farmers market takes place, all summer long down in Minneapolis. So people literally do sit and think, how much money can we make off of this, and how many pounds of tomatoes can we get out of the plants that we're going to purchase. So we've got some Roma tomato plants that have guaranteed tomato yield of 8 pounds per plant, and those are selling for $2 each. And then we have some cherry tomato plants, and those are guaranteed to yield 10 pounds per plant, and those are $3 each. So I'm still thinking about my totals here, and I go back to the beginning, and it said you want to spend no more than $40. So I start by saying, all right, I have 40 bucks. I don't want to spend any more than that. Obviously, I could spend less than that, and I could spend exactly $40, but I don't want to go over that. And that would be in case maybe you're planting too early, you're worried that there might be a frost, you're going to lose your money if all these plants die, so you just say, you know what, I'm going to throw $40 out there right now and see what happens. So there are two kinds of plants that we have here, and that's going to be the Roma and the cherry tomato. And I think I'm just going to have, even though I'd rather not use capitals here, I think that this will work out better if we use it for names. A capital R for the Roma plants, and then maybe just a capital C for the cherry tomato plants, because those are the two kinds that we're looking at. So now I start thinking, that was money. And I know when I set up my equations, I need to have my entire equation about one topic. So I look up here and I think, well, what do I know about money? Well, right here, they said the Roma plants are going to be $2 each. So you can think of that as $2 per plant. That means multiplication. So 2 of the Romas, but probably not going to just buy the Romas. The reason I say that is the cherry tomatoes, it says they yield 10 pounds per plant. And you want some of those too. But they are $3 a piece. So that'll be 3C. So there's our money. And there was another number up there when I was reading through this, and it said for at most 15 tomato plants. Okay, so this one has to be about plants. This first one was all about money, and this one will be about the plants. So I'm looking around, and oh, first of all, it said at most 15 tomato plants. So can we have 14? Could we have exactly 15? Could we have 16? So it can't be greater than. It has to be less than or equal to. And I'm trying to find some more information about the number of plants. I mean, anywhere in there does it say they need twice as many Romas as they need cherries? Do they need 4 more cherries than they need Romas? And you notice there's nothing else up there. You know, it says you want to maximize the pounds of tomatoes you get, how many of each plant should you buy, and that right there tells me I don't know how many of each to buy, which means I know they're going to buy some of each. That's what I know. So we've got one equation about money, we have another equation about plants, and generally this next part is just something that we put in because it just makes sense. Can you have a negative amount of tomato plants? No. So usually we'll say, you know what, let's make sure that both of our variables stay positive. And that's why in real world problems we usually just end up graphing in the first quadrant. Most of the time we're talking about products, and products can't be negative. So this would be in the first quadrant. And we definitely could graph this and find those vertices. Now, what were we trying to do? Because it seems like there's some information here we didn't use yet. Maximize the pounds of tomatoes you get. Well, that's not an inequality. That's called an objective function. The objective function is, what do you want to happen? And what we want to happen is we want to get the most pounds of tomatoes for our money. So I think I'm going to use P for pounds here. And I go back and I try to find out, was there something about pounds in here? Oh yeah, that was over here on the side. Back in this little advertisement. 8 pounds for the Romas and 10 pounds for the cherries. That's what I'm going to try to optimize, maximize right there. And that's called the objective function. So this process, if we were going to do it from start to finish, which we will, just not with this one, we'd start here. We would graph all of those. Now, this has a fancy name. These are called the constraints. And the name makes sense. You know, you have to think constraint is when you're holding yourself back. These are the things that are holding us back. We only want to spend $40. Well, that's going to hold us back. We only want to have 15 plants. You know, you've checked out your garden space and you realize if I go with any more than that, I'm not going to fit them. You know, and they're going to start overcrowding and they're going to die off. And I'm not going to get what I want for the pounds. So this would be the constraints. Once we have those constraints, we graph those. We find that feasible region. We figure out where the vertices are. Pardon me. Then, once we have those vertices, we put those into the objective function to see which of those points will maximize our profit, or in this case, maximize our pounds of tomatoes. So we do know how to do all of this. It's just putting it all together seems like kind of a monster task. So let's start off with some that maybe aren't quite as bad looking. Problem 1 says, testing the vertices. What point in the feasible region maximizes P for the objective function? P equals 2x plus y. So here's my objective function, and I realize that's the last thing I do. That is absolutely the last thing that I do. They give it to me first, but everything else has to come before that. So I have my constraints over here, and that's what I'm going to have to graph in order to figure out where that feasible region is and where those vertices are. So let's color coordinate All right, so I'm going to do mine with the red for that very first constraint up there. And I realize, hey, this is in standard form, so if I just quickly do my zeros, my intercepts should be able to get a decent line out of those. So if we put a 0 in for x, we're going to have to divide by 2 and we'll get 5 halves, which of course we're going to graph as 2 1/2, but 5 halves will leave that perfect. And then if we don't use any of the y's, we have y as a 0, we're going to need a 5. So there's our first line. Now, to do this graphically, you really have to be very careful when we're graphing. So if you have a folder or a notebook or something, you might want to try to make sure that you use something as a straight edge and get that nice and straight. That's way too thick. I'm not going to use that. Now, technically it is a line, but I just looked at the last two constraints up there, and I told myself, you know what, I'm really going to be just focused on first quadrant anyway, because it says x is greater than or equal to 0 and y is greater than or equal to 0. But with standard form, we want to test a point to see where we're going to shade. Pretty quick and easy to just test a 0 and a 0 in here and say 0 plus 0 is less than or equal to 5. Yep, that's going to work. So I need to shade down this way. The other thing you want to do with these is not overshade with a really dark color right at the beginning. And we're going to have like 4 constraints here that we're looking at. So we want to keep it readable. All right, I'm going to switch colors and go to the x minus y is less than or equal to 2. And again, that's in standard form. So using my intercepts would be a really quick, easy way to graph this. So if my x is 0, well, I'm going to have to put a negative 2 in there, because the negative of negative 2 would give me 2. If my y is 0, then my x is going to have to be a positive 2. So I have my 2 points at 0, negative 2, and 2, 0. And again, try to use a straight edge, get things as straight as you can. Because the vertices are what we need to use. We want to be very careful that we're graphing this so that we can see, hey, here's where those vertices are. Still need the shade. Just a 0, 0 in here. 0 minus 0 is less than or equal to 2. Sure it is. So we're going to shade towards 0, 0. And last 2 constraints were x is greater than or equal to 0 and y is greater than or equal to 0. So just so that the instructor would know, yes, I knew those were supposed to be constraints, I would put those 2 on there. But I already know I'm going to be looking at this region right here. That's my feasible region. So far, you should be saying to yourself, we did this last week, Cedar Home. We did. This is last week where we put all this together and we started graphing more than one inequality on the Cartesian coordinate plane at one time. So we know we're not done. We've got to add something to that. And what we need to add is checking the vertices. to find out where do we maximize profit or minimize cost, depending on what they ask for. So I look at this figure and I realize 1, 2, 3, 4, I got myself a little quadrilateral. Quadrilaterals have 4 vertices. Vertices are where the sides come together. So that's going to be at 0, 0. Because we graphed carefully, we can actually see these. And that's going to be at 0, 3. Oh no, that wasn't 0, 3, was it? Mine's looking a little high. Was it 0, 2 1/2? 5 halves? And then we had 2, 0 as a really nice one. And then the one that really matters. And that's the one where we can find that intersection, which looks like that's going to be at 3, 1. Now, why does that matter? Because the rest of them, we could tell from what we graphed originally where they were going to land. But this one depended on our correct graphing of those two inequalities. So if we had to, we could solve the red and the green equations for y, and we could put those into our graphing calculator and find the intersection. But did everybody's look pretty good? Drew it reasonably straight and it looked like we landed there? Then we're okay. So what's another way we could know that we're right with the 3, 1? Well, we could check it. We could pretend that these two constraints set equals and make sure that our 3, 1 actually gives us the answer on the right-hand side. So if we put a 3 and a 1 in here, that's going to give us 5. That's going to work. 3 minus 1 is 2. Good. We know we're right. So we could do it by hand if we had to, or we could use a calculator. But we need to know where those intersections are. So now, what are we going to do with this? Well, now we're at the last step. We're at our objective function, p equals 2x plus y. So what we have to do is take these vertices and put them into p equals 2x plus y and see which one of them gives us the biggest number. Because, I don't want to scroll again, this is so big here. They wanted us to maximize p, whatever it is. Usually it stands for profit. So I'm going to go ahead and put 0, 0 in for x and y. Well, 2 times 0 plus 0 is 0. So that's going to give me a 0. Then I have to put 0 and 5 halves in here. Well, that'll be 2 times 0, which is 0, plus 5 halves, which is 5 halves. But since it is always going to be, these problems are going to be in the form of a word problem, we probably want to write it as 2.5. Our 2, 0, if we put that into this equation, 2 times 2 is 4, plus 0 is 4. So far, that's our biggest number. So far, that would be our max, but we've got one more to try, and that's going to be our 3, 1. 2 times 3 is 6, and 6 plus 1 is 7. We just found our max. Whichever one of those gives us the biggest number is the maximum. Whichever one gives us the smallest number is the minimum. But they only asked us about the maximum. So up here, all of that for answer C. That's why, these, they can be in multiple choice because in the end, you have to do all that math to figure out exactly what's going on. Now, if you're saying, well, we could have just tested all of these in there and seen which one gave us the right one. You can't do that because you don't know for certain which of these points is actually a vertex. So they might throw one in that doesn't make any sense as far as your feasible region goes to throw you off. So 3, 1, a lot of work to get that. All right, down here it says 1a, use the constraints in problem 1 but with the new objective function. So now we're changing this up for a, and we're saying p equals x plus 3y. And they want to know what values of x and y maximize p. I want you guys to go ahead and do that. So use those same vertices. Now, usually we don't get these in multiple choice. My wandered around, it's not most of you are getting an answer there. Usually what we have to do is write a statement at the end about what we found. So we would say the maximum of 7.5 occurs at 0, 5 halves, or 0, 2.5. Because like I said, most of these end up being in a word problem format anyway. And usually, I mean, there's a couple of people in the department that really love this kind of thing. So every once in a while, they'll even just make those two blanks, you know. Ashley. Oh, thank you. There we go. Thank you. All right. Could you find the minimum? Sure. I mean, you've already done the 4 of them. So where's the minimum occurring? Yeah, 0 at 0, 0. So what happens if a business does all of this beforehand and they find out that they're going to lose money? Well, they'd actually get some negative numbers for all of these out here, and they would see that 0, 0 is their best maximizing profit. Nobody wants to work for nothing, you know. So if you do these things beforehand and you have an idea of what's going to happen, things go a lot better for you. So really, they have to do some predictions about what are the costs going to be, what are the different factors that take place in their business. So B says, can an objective function P equals AX plus BY plus C have the same maximum value at all 4 vertex points, Q, R, S, and T? Could it have the same values at R and S only? And then it says explain using values. And that's something that I think if we come back to it tomorrow, everybody would be okay with doing. But visually, let's wait until we've got a couple more of these under our belt before we come back to that. All right. Look at that one, huh? Wow. Okay, a lot to keep track of here. It says using linear programming to maximize profit. So the same thing where we're trying to figure out where would we maximize. And it says you are screen printing t-shirts and sweatshirts to sell at the Polk County Blues Festival and are working with the following constraints. You have at most 20 hours to make the shirts. Kind of a last minute thing, you decided to do it. You're saying, you know what, this is going to be a part-time thing for me at 20 hours. That's what I'm going to have to do this. You don't want to spend more than $600 on your supplies, and you want to have at least 50 items to sell. All right, so we figure out pretty quickly. This is going to be about time. There's going to be a constraint involving time. This one is about money. There's going to be a constraint about money. This one is about the number of items that you can sell. So those are going to be our constraints. So you go over here and you're looking for information, and it says 10 minutes per shirt and 30 minutes per shirt. Well, this is the t-shirt and this is the sweatshirt, so one takes longer than the other. And you realize, uh-oh, that one's in hours. Well, you can't do that. You know, if you're going to talk about time, you have to have those in the same units. So you'd have to take 20 times 60 and get that into minutes so that you can actually come up with a constraint that's going to make sense with this. So the first one we see is going to be 10x plus 30y and then dealing with the 1200. Now, I know they like this table thing, but this kind of drives me nuts because I certainly want to put the plus in there. And then I want to think if I have at most 20 hours, obviously that's less than or equal to the 1200. So I go immediately, to using that total and writing those constraints. The numbers, okay, well, it says you want to have at least 50 items to sell. All right, so I come and look over here. Is there anything about the numbers up here? And I realize, well, no, the rest of the information is about money. So I want some of each, x plus y, but I want to have at least 50 items. So that's going to be greater than or equal to 50. So 10x plus 30y is less than or equal to 1200, and x plus y needs to be greater than or equal to 50. And there was one more constraint, and that was about money. So I look up here and I see, well, this one, we've got the cost at $4, we've got the cost at $20, and it said we wanted to spend no more than $600 on those supplies. So 4x plus 20y has to be less than or equal to $600. Those are my constraints, along with the fact that you cannot have a negative amount of t-shirts and sweatshirts. So when we put those together, we've got our 10x plus 30y is less than or equal to 1200, x plus y is greater than or equal to 50, and 4x plus 20y is less than or equal to 600, but we add these at the end, kind of our freebies, you know, you can't have a negative amount, so x is greater than or equal to 0 and y is greater than or equal to 0. Now, in the end, I have to come up with an objective function. And that objective function comes from the profit. So I look back up here and I think, well, how much money am I going to make from t-shirts? $6 per t-shirt. How much money am I going to make from sweatshirts? $20. So 6x plus 20y is going to be my objective function. And since we're going to maximize profit, probably wouldn't be a bad idea just use p again and say p equals 6x plus 21. That's the last thing we worry about. You know, the rest of it is so important that we figure out where those vertices are, and then we can plug those in and figure out where we're going to maximize our profit. So you'll notice the numbers are a lot bigger in this one. That usually makes it so we're either going to have to use some algebra to figure out where the intersections are, or use our graphing calculator to get that really accurate. So just know beforehand, you know, we'll do the best we can, but it's probably going to be a little off, and in the end we'll have to do some algebra to get it going. Alrighty, so grab one color. Let's get the first one on there. Our first one was about minutes, and that is 10x plus 30y. Needs to be less than or equal to 1200. I'm just going to start with this one in the hopes that, you know, these were some pretty big numbers that I had here. This will probably take care of what I need across my horizontal and vertical axis. And this is in standard form. So I can go ahead and use my zeros and say, hey, if this is 0, this is gone. So 30 times something is 1200. That something is going to be 40. And then if there are 0 y's, take a look at that and realize that's going to have to be 120. So I start to get a feel for what I'm going to need to graph. But usually what I'll do is I will find all of those numbers first before I put anything on my graph. So I just want to make sure I have room for everything to be accurate. So I'm going to switch colors right now and look at the x plus y and 50 constraint. I realize that's a nice one. You know, your zeros are going to be 0, 50, and 50, 0. So still thinking in advance about my horizontal and vertical axis, I realize, well, for my y's, so far my top number is going to be 50, but for my x's, I'm going to need to go to at least 120. But I had one more constraint, and that was 4x plus 20y, so one more color, and that had to be less than or equal to 600. Now I say one more constraint because it's one more constraint that takes some thinking. You know, the x is greater than or equal to 0 and y is greater than or equal to 0. That doesn't take any thinking. We'll just use that as quadrant 1 up here. So if this is 0, we take a look at that and think, okay, well, how many 20s in 600? How many? If y is 0, how many 4s in 600? 150. So now this gives me a really good idea of what I should be doing over here as far as intervals. I want it to be accurate, but I can't go by ones. I'd be here all day, you know. So I take a look at this and say, I've got 040, 050, 030, and I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 little blocks here. So maybe I'll just go by 5s up the side. I'll take care of all of them. I'll be able to see my constraints. But on the other, my x-axis there, I've got to go up to 150. So we definitely could go by 15s. I mean, that would be reasonably accurate. We probably wouldn't be too bad off if we went by 20s. I think it's easier for people if we go by 20s. Get those lines on there. We have to make sure that they're pretty doggone straight, but we need to color code this because in the end, if we don't know perfectly where two of those lines match, we're going to have to figure out their intersection. So I go back to my red for my 040 and my 120, 0. I'm going to do the best I can with the straight edge. Testing with 0, 0 goes pretty fast with this. And really, since it's a word problem, you don't even really have to think about it. I mean, this is less than or equal to, yeah, obviously we're going to be down here. So far, a nice little triangle, but we know we've got a ways to go. Switch colors and go to my next one. 0, 50 and 50, 0. We're using that color coding system so that we can figure out, okay, which intersections do we have to find, either by hand or with the graphing calculator. But that one was bigger than the 50. Remember, this was the shirts that we want to sell. So 0, 0 is not working in this. We're going to have to shade outward on the green. So I start to focus in on the red and green in here so far, realizing I still have one more constraint to have a look at. And so we switch colors one more time. And we have our 0, 30 and our 150, 0. And that one was less than or equal to. So 0, 0 is definitely going to work in that. So I'm shading backwards, but I'm trying to think, okay, what region are we talking about here that would have all three colors? Because that's what we care about. So with me, I'm looking for red, green, and blue. there's good news and there's bad news. The good news is a couple of these, they're easy to find. I already know this one came from my green, so I can go over here and say, hey, that was going to be at 50-0. And from my red, that's going to be at 120-0. I got a couple of vertices up here. No, I was pretty straight with this. This one, maybe we might be able to read that one off and figure out what it is. But this one, that's just kind of iffy. I'm not real sure about where that's going to be. It's possible it landed right on, but I don't know. So now comes the point where you say, okay, would I rather find these intersections algebraically, or would I rather find them graphically? And if we want to find them with the graphic calculator, we're going to have to put all of this into that y equals format. So, let me go ahead and time this so long. I think we can find them. All right, so the first one I'm going to look for is my red and my blue. So I go back to my red, and I realize I'm going to have to subtract 10x from both sides. And then I'm going to have to divide everything by 30. And again, you wouldn't have to reduce any of this if you didn't want to. You could just slap a pair of parentheses around the top, because then your calculator knows to take all of this. But we might as well do a little reducing here. So that's going to be my red equation. And then my blue equation, down here, we would subtract 4x from both sides. And divide by 20. All right, let's get them in the calculator, change our window, and see if we can at least find this one before the bell rings today. Negative 1/3 x plus 40 and negative 1/5 x plus 30. I have to change my window because remember, I know what I had my window set at before. So I had my x's from 0 to 160, and my y's from 0 to 50. Blinky to work. Second trace, number 5, enter 3 times. 75/15. I wouldn't have guessed 75. My graph is off. You know, it just is. And that's going to happen with any of our graphs. So 75/15 is one of my vertices. All right, now I want the other one, and the other one is where my green and blue intersect. So I go back to my green and realize this is a really nice little equation. So all I have to do is subtract x from both sides. And since I don't want Blinky to be concerned about which equation is up there, I'm going to make sure I just use the blue and the green. So I go back to my blue, and that was the negative 1/5 x plus 30, so I'm going to clear that top one and put my negative x plus 50 in there. Graph. And then let Blinky tell me where it is. 25/25? Maybe. I might have been able to get that one off of here. That one wasn't too far off. So 25/25. Like I said, the others, we can just read them off because we already did those as part of the math earlier. So we had our 50-0, And then we had our 120. All the way back up to the top for our objective function, which was 6x plus 20y. And I don't know, bigger numbers, we might want to grab the calculator and punch these in, or we might be sick of doing all this stuff by hand at this point and want to punch it in. So 6 times 75 plus 20 times 15. 750. And then I'm just kind of cheating and hitting second enter because it'll pull this back up. And then I can just change my 75 to a 25. And change my 15 to a 25. And second enter and change this to a 50. And to a 0. And one last time. Punch that one in as 6 times 120. Whew, that's a beautiful problem. We're almost done. Where's max? The maximum of 750, and that would be $750, occurs at 75 t-shirts and 15 sweatshirts. Okay, I hope you're saying to yourself, we've already done all of this before. This is all math we've done. We just never put it together. So 43210 means, I know it's a lot to keep track of, how you're feeling about the whole process. Do you agree with me? It's just time consuming? Yeah, it's not that we don't already know how to do this. So, given that it's time consuming, I'm going to give you a whopping, 4 problems, I think? Oh, some of these you don't have to do from start to finish. Some of these you're just doing pieces of it, like you're writing it. Oh, and this, I don't think this got in your packet. Some people last year had forgotten how to graph this inequality, so I wanted to make sure that everybody remembered that really what we're doing is if it has your x's that way, you're really graphing two vertical lines at -2 and 2. And then because it is between those two, that's where your shading goes. Just in case anybody's feeling a little bit, out of it after 4 days off, which can happen anyway. So tomorrow we will finish this up. Last Wednesday, we had done all the inequality graphing. You just have to use this. You have to use it. Be sure we're able to get some answers for it. And quick reminder, if you didn't check the board,